Welcome back, Calculus. In this video, we're going to be looking at Chapter 5, Section 6. Now, we have done all the U substitution stuff. Good. We have done all the U substitution stuff. We will revisit it again because it is extremely important moving forward with any ideas in calculus that you'll see from this point on. U substitution is going to show up. We're going to use it. Now, in this video, we are going to be looking at 5.6. And the nice thing is that about half of this chapter does not feel calcy. A lot of this stuff is stuff that we've already done in pre-calc. Yes, a lot of it is going to feel just like something we did in pre-calculus. It's almost not going to feel like calculus. In our focus today, we're going to be looking at growth and decay.
Oh, that's kind of existential.
Not particularly. I would consider it more exponential myself. All right. Anyway, as we're looking at this, we're going to be looking at solving a very particular type of differential equation. So solve a differential equation. Now, when we come back from break and we knock out 5.7, there will be a lot of differential equation stuff. 5.7 we'll spend probably the first week after break going over, but we're getting pretty close to finishing everything and being into the review side of things. Okay, so the first thing that we have is, I'm going to try to go through this a little bit less rigorously than your book would, typically. Okay, so looking at this, when you read this thing, dA dt.
The derivative of a with respect to t.
Okay, I would agree with that. It's the derivative of a with respect to t at first. But in context, we don't have a specific unit of time, but that thing is saying how fast does a change as time moves. What are you looking at?
Spring break this
Okay,
week?
spring break is next week, yes.
Oh.
Are we gonna have like a
Like tomorrow's our last day.
winter break packet?
I hope so. Okay, this thing is the change of a with respect to time. That's what this thing means right here. Now, what winds up happening is a lot of the time this thing winds up being proportional to some value.
Are we gonna be having a lesson on
Pi.
Friday?
Pi lesson. Tomorrow's Friday, right?
Yeah.
Okay, so looking at this thing, for this is the typical way that this looks. This is growth. Now, when we're looking at this thing, there are two options. It will be growth if, what do you think is true about k?
Positive.
If k is positive, perfect. What if k is negative?
It's
It's
decay.
decay.
I was totally right about the cancellations.
Not totally.
I would say you're half right.
I was half right about the cancellations.
Maybe even more than half. You were mostly
I'd
right.
say like 80%.
Yeah. All right. Looking at this thing from this relationship that's saying, oh yeah, a changes proportionally with time.
What if it's 0?
What if what is 0?
Okay.
Then there wouldn't be any growth nor decay. It'd just be constant.
When you do real
It will not be 0.
Can we do examples? We should
Constant,
compare it to Dow
constant
Jones.
what?
I'm sorry?
We should do Dow Jones examples.
Instead of growth and decay, can we do bull and bear?
No.
Wait, constant.
Like if it was just constant, it wouldn't be growing, right? It'd just be staying the exact same all the time, be a flat line.
Oh, you mean like constant.
Yeah, it wouldn't be rising, it wouldn't be falling. It'd just be a constant value all the time. It'd be uninteresting. Okay, now from this, check this out. I think if I start with this thing, I can make it so that there's only a's on one side of this equation. What would you have to do, just algebraically?
Multiply by dt.
So if I could multiply by dt and I get, I'll make it lowercase k, a dt. But now I have an a and a k and a dt. Now k is just a constant. I'm not so worried about that k. But I don't like that a being there with that dt.
Divide.
Divide.
Do they cross out?
So they don't just cross out.
Because like I still don't really
Isn't that like a
understand.
natural log function?
Oh gosh, almost. It will be momentarily, yes. Okay. So dA, Sean, just think of it as one quantity itself. Don't think of it as just a, just think of it as dA.
It's really hard.
All right, now looking at this thing, I see a dA over a and a dt. Henry, when you looked at this, you said, isn't that a natural log? Almost. What do I have to do to get a natural log to happen?
Take the integral.
Take the integral. Now, if I take the integral on the left side, where else should I probably take the integral?
Right.
On the right side. Now notice, I didn't have to tell it with respect to which variable. There were already differentials in this problem. A dA and a dt naturally just showed up. Okay, when I do this then, I'm going to go ahead and get the natural log of the absolute value of a is equal to, what's the integral of this thing?
KX.
I'm going to call it not x, kt,
Ooh, let's
plus c.
Can you explain that? Like, what if we took the integral of like 2 dt? Because k is a constant, right?
Yep, so looking at this part specifically, I'm just going to take this guy out. Okay, here it is. This thing, the integral of, that becomes k times the integral of dt, which is k times, well, that's really a 1, right? What's the integral of 1?
X.
Or in this case? Yep.
how do you know k is constant?
We're just going to work on the impression where k is a constant. So we'll even talk about, and I'll even make a little note here, where k is my constant of proportionality, is what we call it.
Well, you spell constant with c.
You do, but I want to make sure that it's not going to confuse me with the other constant based on the initial conditions.
Elementary.
You can call it the constant of variation or the constant of proportionality. They're both going to be the same thing. Now, if that sounds familiar, and hopefully that does sound a little bit ring a bell, because when we looked last year, we talked about things varying directly, varying inversely. And they all had this y equals kx or y equals k over x, all those different things. We've talked about variation before. Now,
If you divide c by k, would just equal c?
it would still be a constant, yeah. Yep. All right. Now, looking at this, we're just going to go ahead and say that for this problem, there's a couple different ways it can work out. Your book does it one way. I would do it a different way. But if you want to actually solve for a, and I'm not so worried about the inner workings of all this necessarily, but let's just say the following. Suppose we are given an initial amount. We are given an initial amount. And specifically, let's say that this is the amount A at time 0, so A of 0, which pretty common for notation, we'll just write A sub 0. Pretty common that we'll use A sub 0 as the initial amount at time equals 0. Okay, notation-wise, does that feel okay? A of 0, we'll just typically write as A sub 0. Okay, now as I'm looking at this, if I wanted to solve for that, I think I would be able to work out at time 0, well, that'd be ln of A of 0, right? At A, like I write just A, but this is really A of t, right? The amount at time t. If I did ln of A of 0, ln of A of 0, well, that would just be equal to k times, what am I plugging in for that t? 0 plus c, and I can see that c is the natural log of a sub 0. Everybody okay with that? Which tells me c is equal to the natural log of, and I'm just going to call it a sub 0 instead. I'm just doing this fancy notation thing so we can distinguish between the two. A of t, I'm just calling a, and a of 0 we'll call a sub 0. Everybody okay with that first little kind of manipulation? If I do this then, and I'm going to keep working, I'm going to come this way.
Just go with that.
I'm sorry?
Just go with that.
But I want to be able to see all this, is my big issue. If I know c is 0, that means, or sorry, c is natural log of a sub 0, it means I would obtain the following. I now have the natural log of a is equal to kt plus the natural log of a sub 0.
I thought you said this wasn't going to feel calcy.
Yeah.
It will for right now. This part shouldn't feel very calcy. This just feels like algebra.
Not really. There's a lot of calc stuff.
We've done one calc thing.
The integrals and like, with respect to and
Yeah, we took the integral, and then that was the only calc we did.
technically, yeah.
The best kind of correct. Okay, so looking at this, could I solve this thing for a somehow, do you think? Just for this a. So I could do e first. And I certainly could, right? I could do this. I'm going to hold off, though, because that makes the right side of this equation look awful.
How is that coming from?
I'm sorry?
How is that coming from C equals
I just replaced this C with the natural log of A naught. Okay. Instead, first, I'm going to kind of push us along in the right direction. I could do this. I'm just going to subtract A sub naught, or A naught, from both sides. Just doing a little bit of algebra. Nothing too crazy, even. From this point on, and I'm going to try to make sure everybody can catch up with writing stuff. Gosh, that minus in between those two logs sure looks familiar to me.
Oh my god, that's like f of b minus f of a.
So that's not a
Writing, right?
bad idea, but we can rewrite it somehow.
Is it incorrect? It's, oh my god.
It's not going to be the natural log of A minus A naught, A over A naught. My next line then gives me this.
Oh, I forgot.
That's a natural log property.
That is a natural log property. Perfect. At this point, if you want to undo the natural log, if I try to take E, base E, exponentiate base E, if you want to use the correct language, both sides, is it as ugly?
Oh, like e to the whatever.
Yeah. Like what happens when I exponentiate here? A over A naught is equal to E to the KT. And one last little step here, we're just going to solve this thing for A. And I promise that there's a reason we did all this. What I'm really after in this problem is being able to say with confidence that A is equal to, well, I'll just say it's A naught, E to the KT.
Okay, this is what we were looking for, right? We don't have to like do all that again?
Correct.
Okay.
This is like 8 per.
This is exactly like a pretty good deal, right? PE to the RT. Or it's like AE to the KT if we looked at exponential stuff last year. This is the exact place where those formulas come from.
When you say last year, do you mean pre-calc?
In pre-calc.
I-
Yep.
okay.
Do you remember doing PE to the RT?
I know it, yeah, I remember doing it. I don't remember what we used it for.
So that's compound, continuously compounding interest.
Oh,
Yep. But we also did like exponential type problems, like, oh yeah, here's a population with this much at this point.
Like the bacteria.
Yeah, we did the bacteria problem, and I bet we do a similar problem here in a second. Now, the nice thing about this is we've never seen where this came from before. Before it was just me saying, oh yeah, here it is. All we have to say is, oh yeah, the rate of change of some quantity is proportional to something. And this is all the math that goes into getting this formula, whether it's PERT or AE to the KT, whatever the case is. Now, as Sean pointed out, what's going to happen is we now have the ability to, if we recognize a problem is just varying proportionally, we can jump straight to here. And we can just take that shortcut. We never have to do all this integral stuff again. With that said, let's do a problem.